In this section, we're going to cover, or in this video, we're going to cover section 4.6, integration techniques, using the method called integration by parts. So like the method of substitution that we covered in section 4.5, this is another way of finding an antiderivative of a function that doesn't work by a quick formula. So we're going to learn how to evaluate integrals using the formula for integration by parts, and then solve applied problems using integration by parts. So we talked about section 4.5 on substitution. We said at the end that it was reversing the chain rule. Integration by parts is the reverse of the product rule. All right, so here is our formula. The integration by parts formula says that the integral of u dv, so we're going to be given a problem, and within the problem we're going to have to pick part of it to let equal u, and then pick another part of it to let that part equal dv. So u dv equals u times v minus the integral of v du. So if we're given this, we can identify u, so we'll have this piece. We'll need to find the derivative of u, so we have this piece, that's the du. Okay, from our original, we'll also identify what we are going to call dv. So we'll have to get back to know what v is, because we're going to need it here, we're going to have to anti-differentiate the dv. So whatever you pick for u from the original, you'll have to find its derivative. And whatever you pick for dv, you're going to have to find its antiderivative. Okay, it'll take some practice. It's a little confusing at first, but we'll practice it here. All right, so tips on using this formula. So if you had no success trying substitution method, that means we're going to resort to trying this integration by parts. So in other words, if the substitution method from section 5 doesn't seem to work out, then maybe parts is a better option. 2, use integration by parts when an integral is of the form f of x, g of x, dx. Okay, in other words, match it with the form of that u dv. Okay, so it's a product of something usually. Not always, but usually. So part of it's going to be represented by u, the other part by the dv. By choosing some of it to be u, so say the f of x is the u, and that f of x you have to be able to find the derivative. And the remaining part, the g of x dx, or the rest of it, will be assigned to dv, but the thing is, on the dv, you don't want to pick something that you can't integrate, because you have to be able to find the antiderivative or integrate that. So that'll kind of eliminate some choices as we go through these examples, because some things can't be easily integrated. All right, find du by taking the derivative of the u, and then find v by integrating the dv. If the resulting integral is more complicated than the original, remember the formula was uv minus the integral of v du, so you'll still have an integral to evaluate. If that's more complicated, then start over and choose something different. And then we could always check our solution at the end. All right, so let's try this example. Evaluate the integral of the natural log of x dx. All right, so we cannot just write down the answer here, because we know the derivative of natural log, right? But it doesn't have a direct antiderivative. Okay, so we're going to treat this as a parts problem. So we're going to choose, anytime a log is involved and you're using parts, you always want to let your log expression be your u, because if you can't integrate it, it can't be the dv part. So if a log is involved, that's another hint here on integration by parts. If you see a log involved, that should be your u assignment. So we're going to let u be natural log of x. And the only other thing I have here, so all the rest of this is just the dx. So that means dv equals dx. So from the original problem, you pick something to be u, and everything else is dv. Okay, then you take the derivative of u. So du, just like from substitution, is 1 over x dx. And you integrate this. So if this is just the antiderivative of 1, right? It's just v and then the antiderivative of 1 on this side is just x, because my variable here is v and the variable here is x. Okay, then the formula says u times v minus the integral of v times du. So you just got to memorize that. uv minus integral v du. Okay, so once you've written all that stuff down, just fill it in. So this is just natural log of x times x minus, and then this is the integral we have to evaluate. Before we're going to evaluate, we're going to clean it up. So we're going to cancel our x's, simplifying that to just 1 dx. So the antiderivative of this thing is just x, right? The antiderivative of 1 is x plus the c. So we get x natural log of x minus x plus c. All right, let's try another one. Evaluate the antiderivative of x e to the 3x dx. All right, so we're going to let u equal x, and we're going to pick dv, right, from the original. Part of it is u, so we're going to let that be the x, and then e to the 3x dx, everything else is going to be our dv. All right, so the derivative of u, right, so du would just be 1 dx. Antiderivative here will get me v, so the antiderivative of this is e to the 3x divided by 3. Okay, so then I take u, which is x, times v, u times v, so x times 1/3 e to the 3x, minus the integral of v, which is this, du, which is the dx. Don't forget, you still have to evaluate this, so this part's just what it is, x over 3 e to the 3x minus 1/3 just stays in the front. This antiderivative is e to the 3x divided by 3, so that's where the 9 comes from, plus c. Okay, let's try another one. Antiderivative of x, natural log of x, dx. Okay, so I know on the last problem, we let u be the x and dv be the rest. But remember, we said at the beginning, when the logarithm is involved, you have to let that be your u. So I think on this one, they're going to walk you through different choices, so if you were to make wrong choices, you would know why. So let's examine several different choices and figure out if they're going to work or not. All right, so attempt 1. So let's say we just said, let's let u be 1 and just dv be the whole thing. First of all, that will never work out, okay? That's never a good idea. Okay, if you could integrate x ln x dx, you wouldn't even be using parts in the first place. You would just write down the answer, right? So you never want to let dv be the whole thing because you have to integrate it. And if you could integrate it, you wouldn't need to be doing the integration by parts, okay? All right, second attempt. Let u equal x ln x and just let dv equal the dx part. Okay, the problem here is you can differentiate this, but you have to use the product rule. So the first function times the derivative of the second plus the derivative of the first times the second. Okay, and then the antiderivative of dv is v and the antiderivative of dx is x. Okay, so when I plug all that back into my formula though, u, which was this, times v, which was x, minus the integral of v, right, which is x, times the du part, these would cancel, right, this would be my du. Okay, the problem with that is this thing that now I have to integrate is more complicated than the original, right? I didn't simplify anything. Okay, the goal is for that new integral to be a simpler integral. All right, so that's really not helpful. All right, so let's try this way. Let u just be the log part, and that's kind of always sort of your default. If a log is involved, let that part be u, and then everything else should be your dv. So let's let u be the natural log of x, and the dv be everything else, which would be x dx. Okay, so the derivative of u, 1 over x dx. Antiderivative here would be v, and this would be x squared over 2. Okay, Then plug into the formula, u, which is ln x, times v, x squared over 2, u times v, minus the integral of v again, and then times the du part, which was the 1 over x dx. Notice here, when I clean this up, 1/2 can be brought to the front. X squared over x is just x. So 1/2 the antiderivative of x. This is simpler, right? So that means this was helpful. So I can integrate this easily. So I would leave the 1/2 in front. I get x squared divided by 2. So there's another 2 on the bottom. That's where the 4 comes from. This is just what it is. X squared over 2 ln x minus, this was my antiderivative, plus the c. All right, how about a definite integral with parts? Now, if you notice, this, just the integral of natural log of x dx was the very first example that we did. So we already have done that integration by parts. We already found the indefinite integral. Now we just need to evaluate it. So if you hadn't done the antiderivative or the integration by parts method for natural log of x, you would do it, right? If you go back to our first example, this, whenever we did it, we got this answer. And then we just use our limits to plug in and subtract. So 2 ln 2 minus 2 minus 1 ln 1 minus 1. Plug in the top, plug in the bottom, subtract the results. Natural log of 1 is 0. Distributing the negative makes that a plus 1. And cleaning that up gives you 2 natural log of 2. Negative 2 plus 1 is minus 1. And the calculator should verify that that's 0.386. So if you have a definite integral for parts, you just do the parts method, get the answer, and then plug in and subtract exactly like we have been doing this whole chapter. All right, so evaluate the integral from 0 to 7, x squared e to the negative x dx, to find the area of the shaded region shown below. Right, we've already talked about that the value of the definite integral represents the area under the curve. Okay. All right, so let's let u be x squared and dv be the e to the negative x dx. So the derivative of u is 2x squared dx. The antiderivative would give me v, so this would be e to the negative x divided by the negative 1. That's why the negative is in front. Then use your formula, u times v minus the integral v times du. Okay, so we get negative x squared e to the negative x here. These clean up to be a plus. 2x, we still got this e to the negative x dx. All right, this is simpler because before we had an x squared and an e to the negative x, right? But the problem is it's still a product, so we still have to use parts. So we have to do parts again to evaluate this. So if we're doing this part here, we're going to let u be the 2x and let dv be the e to the negative x dx. So du is just 2dx, derivative of this. dv, antiderivative would be v, antiderivative again, e to the negative x divided by the negative 1. All right, so just for this piece of it, u times v minus the integral v times du. So we get negative 2x e to the negative x. This should be, okay, they've already evaluated here. So that would have been a plus, right? The 2 would then stay, and then you'd get e to the negative x divided by the negative, so it turns back into a minus when you evaluate it. Then you can substitute that back into its spot on our answer. So this, we had this minus this, right, that plugs in there, and then you end up being done, right? This was the first part of that first parts, and then this was the evaluation by parts for that second integral. So it's not really convenient when you have to do it twice because it's kind of a time-consuming, maybe confusing process, but sometimes it is necessary. Right? Next step here, they just noticed that they have a factor that they could factor out, and they did that. So they factored out a negative e to the negative x, leaving x squared plus 2x plus 2. Right? So that was our result, right, from all the doing the parts twice. This was a definite integral, so we do all of the anti-differentiation, and then we can evaluate by plugging in 7, plugging in 0, subtracting. And then that cleans up to be negative 65 e to the negative 7th plus 2, or 1.94. All right, so this next example, x cubed e to the x dx. So remember the one we just did had an x squared and then an e to a power? This one has an x cubed. So when we had an x squared, we had to do it twice. So most likely, because there's an x cubed, it means we're probably going to have to do it 3 times, right? So if I didn't really like doing it twice, it's not going to be fun to try to have to do it more than that. Okay, so when you have a situation like this where you have x to a positive power times e times an exponential, there's a shortcut for when you have this power higher than 1 right here. It's called the tabular method, okay? And it can shortcut your work and not have to go through parts multiple times. That only works on this type of a problem, x to a positive power times e to a power of x. All right, so this is how it works. You take your x to the power, in our case it was x cubed, and you differentiate it as many times as it takes to get 0. Okay, so if you had a positive power of x here, eventually you're going to get it down to a power of 0 if you keep taking derivatives. All right, so the first derivative is 3x squared. Then this function's derivative is 6x. This function's derivative is 6. And then this function's derivative is 0. So that's how you know when to stop, when you get 0. All right, you'll have a sign pattern that you'll have to use to connect them. It'll always be start with a plus. So plus, minus, plus, minus. You attach a sign to every derivative except for the 0. You just alternate how many times it takes. Then your dv part, which would have been e to the x in this problem, gets integrated the same number of times as you had to differentiate to get a 0. So if you had e to the x as your dv, the antiderivative is itself, the antiderivative is itself, the antiderivative is itself, the antiderivative is itself. And I know to stop here, you do this first to get to 0, and this is done the same number of times. Okay? Then you just match up. So you take this first derivative here, this first function that you started with here, your u, and you match it with 1 box lower in the antiderivative column. Notice it goes through that positive sign right here. Okay, do the same all the way down. Next number matches with 1 below. It goes through the negative box in the middle. Then the 6x matches with the 1 below. And then the 6 matches with the 1 below. Okay, so you're going to multiply x cubed by e to the x and make it positive. So you're going to get x cubed e to the x. Then you're going to change the sign, minus 3x squared e to the x plus 6x e to the x minus 6 e to the x. Okay, you just match them up. Add the products along the arrows. Products meaning multiply the two things that are connected by an arrow, making the alternating sign changes to obtain your answer. Those were matched up. Then there was a minus sign, these were matched up, then it was a plus sign, these were matched up, then a minus, these matched up, and then finally your plus C. So that's way faster and way more convenient than having to do parts 3 times. I could have done the same method for the previous problem where I had to do parts twice. I could have shortcutted it to this method instead. All right, so our summary for integration by parts. It's reversing the product rule. Your formula is you start with the integral of u dv. By differentiating u, integrating dv, you end up getting u times v minus the integral of v du. The choices for u and dv should be such that this integral is simpler, right? This one that shows up here is simpler than the original. And if that does not turn out to be the case, you need to try something different. And then our tabular method, the one we just finished, is useful in cases when you would have to do repeated integration by parts. Okay, this will take some practice. All right, if you have questions about it, don't feel bad about having to ask. All right, so I am here to help you if necessary. All right, so that is the end of section 4.6.